All right, Brian here, and we're going to continue our study of the material of Chapter 3 by thinking about, which is motion in two dimensions, by thinking about circular motion. Okay, and circular motion is another type of motion in two dimensions. Now, we've talked about acceleration this way. Acceleration is equal to change in velocity divided by a time interval. We know that that's true, but velocity is a vector. Direction makes a difference. And so as a consequence, if you're changing direction, that is an acceleration just as clearly as changing speed is. And some animals, like the cheetah here, really excel at changing speed. But other animals, like this rabbit here, really excel at changing direction. You can see it's turning a corner, and it has finished turning the corner before the cheetah has. And the high acceleration, not in picking up speed, but in changing direction, is what allows a rabbit to evade prey. That is another strategy. Now, the particular type of motion with changing direction we're going to look at is circular motion, and it turns out lots of different types of motion where you're turning corners, but also walking. We'll come back and talk about that. We can think of as basically being circular motion. And if I have an object moving at a constant speed v in a circle, the acceleration is a vector directed towards the center of the circle. That's going to be important for us. And the magnitude of the acceleration is just given by the square of the speed divided by the radius of the circle. The acceleration is equal to v squared divided by r. And let's look at an example here. And it turns out when you turn a corner, you turn your wheel at a certain angle, you basically follow an arc of a circle. Okay, during your turn around the corner, you're basically following the arc of a circle. And I measured this out. I did a Google Maps image for like going from LaPorte Avenue to College Avenue in downtown Fort Collins. You go around an arc of a circle that has a radius of about 30 meters. We can use that to do some calculations. But I want to think about this. Suppose your car is exactly at the midpoint of the turn. You are right here. What is the direction of the acceleration vector at that midpoint? I want you to think about it for a second and think which one of these four choices is the correct one. Take a minute. I'll be back. Well, as your car is making this turn, you are describing the arc of a circle. And so the whole circle would look like this. And you don't do the whole circle. You just do a piece of it. And at the midpoint, the acceleration vector is directed towards the center of the circle. And that's going to be crucial for us. I want you to remember that. And when we get to talking about forces and talk about circular motion, we'll come back and discuss that. And I want to look at an example of animal locomotion. And we're looking at racing greyhounds. And racing greyhounds are really, they have some amazing physical attributes. One is amazing acceleration. Two is amazing cornering abilities. And here is actual data from like racing greyhounds. They run around tracks, and the tracks are 45-meter diameter semicircles. Okay, and a typical speed for a greyhound in a race is about 15 meters per second. So my question is, as a greyhound is in the turn, what is the acceleration in meters per second squared and in units of g? So first, let's do some strategizing. And for strategizing, we're just going to talk about this. What type of motion is this? Okay, and we're going to assume that the greyhound is basically going through an arc of a circle. It's going through half of a circle. Okay, and so we're going to treat this as an example of circular motion. And in the middle of taking the turn, it's going in a circle. It's got a certain acceleration. It's directed towards the center of the circle. And we are going to solve for the magnitude of the acceleration as the greyhound is taking that turn. Next piece is to prepare. Well, the magnitude of the acceleration is just equal to v squared divided by r, and we know what v is. Okay, we know what v is, but we don't know what is r. Now, it's a 45-meter diameter semicircle. Okay, so the semicircles look like this, and from here to here is 45 meters. And so the radius is just half of that. The radius of the turn is 22.5 meters. And with that information in hand, we can solve. The acceleration is equal to v squared divided by r. That's equal to 15 meters per second squared divided by 22.5 meters. And if we solve that, we end up with an acceleration of 10 meters per second squared. And our units check. If I take meters per second squared, I get meters squared over second squared. I divide by meters, I get meters per second squared. Everything works out nicely. That's my acceleration. Next piece is we're going to assess, does this answer make sense? And the acceleration that we're getting of about 10 meters per second squared is comparable to the acceleration we saw for a lion who was like starting a sprint. It was about 10 meters per second squared. And it turns out land-dwelling animals can't do accelerations much bigger than that for reasons that we'll talk about when we look at forces. And so this number squares with things we've seen previously. And so my assessment is this is reasonable. And now I want to give you a preview of something we're going to talk about when we get into chapter 5. And this is kind of an amazing thing. The greyhounds don't slow down when they turn corners, and you do. And this is one of the things that makes them such amazing racers. When human beings turn corners, they have to slow down. Greyhounds do not. And the difference is something that we'll talk about when we get to chapter 5. So this is something we'll return to. But I want to talk about what we're doing next and the in-person segment in class. In this shortened Labor Day week, okay, we're going to have one class and we're going to do it on Wednesday and we're going to do it on Friday, and you're going to go to one of those classes. And I want to treat something that, and it's based on the idea of relative motion. Now, relative motion is something you're going to read about in the chapter, and you're going to have a chance to think about it in your recitation section and also on the homework. So the ideas of relative motion. So read about it, think about it in recitation, think about it for the homework. And once we've talked about relative motion, it's going to open the door to what's called the theory of relativity. And that has to do with the theory of space and time. And we can actually get to a point where we can answer this question this week: is time travel possible? And I wanted to show you something early in the class that is just truly mind-blowing. And this is something that's a bit of an obsession of mine, and I'll be happy to share that with you next week.